Good day. This would be the lecture for the sample problems for 2 force and 3 force bodies. Remember from our previous lecture, 2 force body is defined to be a member or a body wherein all of the forces acting on the body is only acting at 2 points. So when you have that kind of body, you can simplify the resultant of all the forces acting on that body into two equal and opposite, equal in magnitude, opposite in direction, but same line of action forces. So here is a problem that would illustrate the concept of a 2-force body. So here is our sample problem 1. The magnitude of the reaction exerted on the L-shaped bar at P is 60 pounds. What is the magnitude of the reaction exerted on the bar by the support at A? Also, what are the X and Y components of this reaction? So, if you can see, at point A, this is a pin support here. And at point B, you also have a pin connecting the bar to a plate. So we're just concerned with the bar. If you examine the bar is connected at 2 points, point A and point B. There is no weight given for the bar. There are no external force applied on the bar. It means that since there are no external forces and there's no weight, the forces acting on the bar is only at point A and at point B. Hence, the bar is a 2-force member. So how will we solve the problem with that notion? So we draw the FBD of the bar. Supposedly, the bar is supported by a pin at A and a pin at B. So supposedly, if you do not know the concept of a 2-force member, for pins, you would put two forces, AY and AX. These are assumed directions. You can assume the direction to be downwards. You can assume the direction to be to the left. But these are our assumed directions. We would also be placing a force along X on B and a force along Y on B because the bar is connected to the plate by a pin. So this is our FBD. And note that the 60-pound magnitude force in the given is not By, it's not Bx. It's actually the resultant of By and Bx. So, how will we consider this as a 2-force member? So, this would be the bar would have 2 points, A and B, where the force is exerted in. You connect those 2 points with a line, and the two forces, the two opposite in direction and equal in magnitude forces would be acting along the line of action here. So instead of having 4 unknowns, By, Bx, Ay, and Ax, we will now have just one unknown, Fab. Of course, you would be able to know the direction uh, of the bar, of the force rather, because of the given dimensions of the bar. So we know that from the given, Fab is 60 pounds. And then the given dimensions from the previous slide, you can go back to that slide. The x component is 14, and this direction, this downward direction, the measurement is 17. There. So, summing forces along X, AX would be equal to FAB times 14 all over square root of 14 squared plus 17 squared. And that would be 38.1424 pounds. The direction of the force along X is to the left here. And take note that this force FAB, that would be the resultant of AY and AX. So the X component of AB is equal to AX and the Y component of AB is equal to AY. But since we assume FAB, there's no mention in the problem if it's tensile or compressive. We assumed FAB to be tensile here, away from the point, going away from the point. Then AX would be to the left, AY would be downwards. Now, we go to the concept of a three-force body. So, it says there, the definition of a three-force body: a rigid body subjected to forces acting at only 3 points is called a three-force body. So, if for a two-force body, the resultant of all the forces acting on the body would be simplified into two forces with equal magnitude and opposite direction in the same line of action. For a three-force body, the three forces are either concurrent at a point or parallel. So what would be the use of this notion? So if we know the direction of two forces, say we know the direction of F3 and we know the direction of F2, we can simply connect their lines of action and get the point of connection, and we would get the direction of F1. F1 would be, the direction of F1 would be from its point of application here up to the point of concurrency of the line of action of F3 and F2. Now, if F3 and F2 are parallel, so they would not meet. The two lines would not meet. It means that F1 is also parallel to F2 and F3. Okay? So, here is a sample problem on the three-force member. So, the weight W is equal to 40 Newton, acts at the center of the disc. If the surfaces are rough, what force F is necessary to lift the disc off the floor? Okay, so take note of the given. The disc is flat, is lying on the surface that is indented at this point here by 50 millimeters from the ground. And then you have your weight acting at the center of the disc. And then you have your radius, 150 millimeters, and you have a cord pulling the disc. So what happens is, when you pull on the rope F, the disc will roll, and the disc will not be able to be in contact with the ground. But it would be in contact with this point. So how would we draw the FBD of the disc? This is the disc, and this is the point here. This point here is where your the indentation on the ground is in contact with the disc. So of course, we place the weight at the center of the disc, and then we place the force F from the rope tangent to the disk. Since in the previous figure, there's no mention of whether it's below the circumference of the disk. So we assume it to be tangent to the disk. And then, we place forces here at the point where the disk is in contact with the ground. So we place a normal force and we place a frictional force since the problem mentioned that the surface is rough. Now, supposedly in the figure, we saw that the disk should be in contact with the ground here at this point. However, since the target of the force F is to lift the disk off the ground, once the disk is lifted off the ground, there's no more contact with the ground at this point. So we will not place any force at that point. Okay? Then how do we use the concept of the three-force member in this problem? Take note that we know W. We know the weight of the disk. We would like to find F. So what is F? But we also do not know N and P. We only know their direction. So how do we solve this force using the concept of three-force member? So take note that these are the two forces that we know the direction of. The weight is always directed downwards, and the force from the rope is tangent to the wheel. So note that the wheel is subjected to force at 3 points only. Here, for force F, at the center of the disk for W, and at this point here, where the wheel touches the indentation in the ground. So the wheel is a three-force member, even though it can feel 4 forces here. So what is the repercussion of the wheel being a three-force member? So we see F here with a known direction and a known point of application. We also see here W with a known direction and a known point of application. What we will do would be to connect the line of action of W with the line of action of force F. So a horizontal line of action and a vertical line of action connects at this point. And then, the third force is acting upon this point here. This point here. So this is the point where the third force is acting on. We connect that point of application of the force to the intersection of the line of actions of F and W. So with the definition of the three-force member, if the forces, since F and W are not parallel to each other, then the third force must be concurrent with the line of action of F and W. It means that the line connecting the point of application of the force here in this portion and the intersection of the lines of action of F and W would be the line of action of your third force. So we can now get the resultant of N and P, and that would be R here. So the resultant of N and P is R. But the magnitude is not N plus P is equal to R. Take note. We have the vector notation here. So the resultant of N and P is directed along this line of action. The connection of the point of application of the force and the intersection of F and W. So what happened was, initially we have 3 unknowns, N, P, and F. But now, we only have F and R. We reduced N and P to 1 unknown. with a known line of action. So how will we solve the problem? We actually don't know yet the angle of R. So how will we find out R? So again, here is the diagram showing the three forces. Your F, your W, and your R. And we take note of the given. So again, the indentation from the ground is 50 millimeters from the ground along the y-axis. And the radius of the disc is 150 millimeters, hence its diameter is 300 millimeters. So our target would be to find out the angle of R either with respect to the horizontal or with respect to the vertical. So how will we do that using this given? Take note that whenever you connect a point on the circumference of the circle to the center of the circle, it's always the radius. So the length of this line is 150 millimeters. Okay? And then you note that the length of this line from the center of the circle here up to, again, the circumference is 150. Since this length here is 50, the remaining length would be 100 millimeters from the center up to this line here. And so, we consider this triangle, there. The hypotenuse is 150 millimeters. The one side is 100 millimeter. So when we determine the other side, L, we use the Pythagorean. L squared plus 100 squared is equal to 150 squared. So we get L, 50 square root of 5. Where will we use L? We next consider this larger triangle. Okay, so I told you we need to find the angle of R of this force with respect to either the horizontal or the vertical. So it's either this angle here or this angle here. So we label the angle here at the top of the triangle as theta. How will we get theta? Note that we already have one side of the triangle, which is L. And then, this larger length of the triangle, from this point up to this point, there, would be 300 minus 50. So since we know L, which is the opposite side of theta, and 250, which is the adjacent side of theta, we can now solve for theta. Theta is opposite over arctan of opposite over adjacent. So we solve for theta. Theta is 24.0948 degrees. Once we get theta, we can now solve for R and F with W. So we just first sum force along y equal to 0. So that's R cosine theta, since theta is with respect to the y-axis, minus W, since W is downward. We get R, 43.8178 newtons. And then, summation of forces along x, R sine theta minus F is equal to 0. We get F. The value of F is 17.8885 newtons. And that's what we are looking for. Okay? So if you would have any questions regarding these problems, you may consult with me. Now, I'm sure you had a hard time with the geometry of the previous problem. And actually, considering three force members and the concept of concurrency of the three forces would really give you a hard time in geometry. So instead of delving into geometry, you can actually not consider the concept of the three force member. But the two force member is important. So in this case, in this problem, determine the reactions at A and the force experienced by member BD if the suspended load weighs 600 pounds. So if you will see the angle bracket ABC, it is pin connected at A. It is connected to member BD by a pin B. And it has a weight at C. So it is a three-force member. But we will not be using the complicated geometry in solving the forces. Do take note first that member BD is a two-force member. Why? Because it's pin connected at D and it has a pin connection with ABC at B. There's only 2 points wherein the forces of BD are applied to, hence BD is a two-force member. And since BD, points B and D can be connected by a horizontal line, the force along BD is horizontal. This is actually your bar or your short link. So what will we do? Instead of drawing the whole body diagram of ABC connected to BD, we would be drawing the diagram of ABC. So I placed the figure here for us to be able to refer to the given in the figure. So this is your angle bar ABC. There's a 600-pound load at C. And then, there's a pin connection at A, AY, and AX. And then, there's a two-force member FBD connected to point B. So again, we know now the direction of FBD. It is horizontal. Now, the direction of FBD I drew in here is assumed. You can assume FBD to be to the left or to be to the right. This assumption, since the force is going away from the point, this is tension, assuming that FBD is under tension. If I assume FBD to be towards the right and going towards point B, then that would be compression. So instead of going through the complicated geometry of finding concurrent points and connecting point A to the point of concurrency of FBD and W, what we will do is simply to apply our equations of equilibrium. So normally, the first equation of equilibrium that we apply is the summation of moment at A. Why? Because when we saw moment at A, AY, which is an unknown, as well as AX, do not have a moment at A. Hence, if they do not have a moment at A, then they will be out of the equation. And we would be able to solve for FBD immediately. So, summation of moment at A, the 600-pound force is downwards. Hence, it would have a clockwise moment about A. And the distance of point C, the horizontal distance of point C from A is 3 feet here, 3 feet, plus 4.5 times cosine of 30. So this is the hypotenuse, cosine of 30 is the adjacent side. And then FBD would have a counterclockwise moment about A, and the distance between point B and point A, the vertical distance, is 3 because the angle of AB is 45 degrees. Hence, if BD is 3 feet, then AD is also 3 feet. And as you can see, we only have one unknown in this equation. You would be able to solve for FBD. And since the value of FBD, the magnitude that we were able to solve for FBD is positive, then it means that we were able to assume the right direction of FBD. And instead of writing to the left, we write tensile. That's what we do for two-force member. We assume that the two-force member is under tension or compression. Next, we sum forces along X. So we only have two forces with components along X. That would be FBD and AX, and they would be equal. And then AX would be directed to the right. We also sum forces along Y. We only have two forces along Y, AY and W. So AY would be 600 pounds. Okay? Directed upwards. Always indicate the direction of the forces in your answers. Last, for the last sample problem, L-shaped bar is subjected to loading as shown. Determine the reactions at A and the force experienced by member BC. Are the three forces acting on the L-shaped bar concurrent? Is the L-shaped bar a three-force member? So, we note that for the L-shaped bar, there is a pin at A, a pin connection at B, and a force at this end. So, if we really consider the member, all the forces plus the moment is only acting on 3 points, A, B, and this end here. However, the limitation of the definition of the three-force member is it should be subjected only to forces, not to couple moments. So since there is a couple moment of 3 kilonewton meters at this end, this cannot be considered as a three-force member. However, BC is a short link, it is a two-force member. So even if you see a pin here, you see a pin connection at C, do not put CX and CY. You would be putting FBC with a known angle, known direction. So the FBD of the L-shaped bar, 2 kilonewtons, 3 kilonewton meter couple moment. The FBC, again, we assume to be tensile. And then the forces on the pin, AY and AX. So the first thing we do, again, is to sum moment at A to get FBC. So take note, 2 kilonewtons clockwise, negative, times distance. I converted the 0.5 to meters because of your couple moment. It's 3 kilonewton meter. So to be consistent with the units, I converted the lengths to meters. And then for FBC, take note of the given. The vertical length is 150 and the horizontal length is 250. So this is what I used in obtaining the x component for BC, because the x component of BC is the one that has a moment at A. And then don't forget the distance, 700 or 0.7 meters. So this is one of the common mistakes and one of the common carelessness I have observed in checking ES11 papers and even ES13 papers. When they multiply this large value or term to the force, they often forget the moment arm. So remember that we are summing moments. Of course, for the 3 kilonewton meter, you do not need a moment arm. So we get FBC to be 6.6639 kilonewtons. And since we were able to get a positive value again, it would be tensile. And then, we sum forces along X to get AX. So AX is 5.7143 kilonewtons to the right. And lastly, we sum forces along Y to get AY. And AY, that would, I'm sorry, this is a typographical error. That should be AY. AY is 5.4285 kilonewtons upwards. Okay? So that would be for this part of the lecture.